Hello everybody and welcome back. We're looking at question number 9 on the 2008 Euclid contest. So the equation 2 to the x plus 2 times 5 to the 6 minus x equals 10 to the x squared has two real solutions. So this is nice that they're actually telling me how many solutions there are. That means, if I get two solutions, I know there won't be any more. And we're just being asked to determine these two solutions. Okay. Now, the thing I would draw your attention to here is them saying real solutions. This doesn't always matter, but sometimes it does. Real solutions means that things that we tend to take for granted, especially in early high school or late middle school or late public school, they don't really apply. So a lot of times when you see expressions with exponents, you'll often see, 2 to the 3 and, 5 to the 6. It's integers all around, okay? But, and you probably could, there's two real solutions. Neither of them might be integers. No, 2 will work. But you can fool yourself into thinking, well, these must be integers, and therefore I can make this assumption, therefore I can do this. Okay? One of the solutions could be root 3 times pi, or I don't know, pi to the 125, something weird that you wouldn't expect. And sometimes when we make assumptions, when we see setups that are quite similar to simpler things that we've seen in school, and we ignore the real solutions part, we can make assumptions, or we can just say, well, no, that clearly couldn't happen, that possibility is irrelevant. That can cause us problems. Now, it's not going to be so bad in this question, because they actually told me how many solutions there are. But if they didn't tell me, how many solutions there are, they just said, find all real solutions to this, and I started making some silly assumptions about integers or something like that, maybe x equals 2 is the only one I'll be able to find, and there's some weird one where it's x is root 3 times pi that I'm completely ignoring because of some of the assumptions I make. But it's not going to be too much of an issue here because they told me how many solutions, and they did remind me they can be real. Okay? And as I've said, I just plugged them into my head. X equals 2. I just sort of found that one out. How did I find that one out so quickly? Well, one of the assumptions you might make, if you're assuming that all of these are nice and integers, is that 2 times 5 is 10, right? So this one here has to be the same as this one here, has to be the same as x squared. And so we solve this system, and it will only have x equals 2 as a solution. Okay? But that's making a bunch of assumptions. That, 2 times 5 equals 10, so it must just be the case where I've done something like 6 to the 3 is 2 to the 3 times 3 to the 3. Okay? But that doesn't have to happen. Okay? With real solutions, you can have very, very odd things happen. Alright, so it's 2 to the x plus 2, 5 to the 6 minus x is 10 to the x squared. Now, I still will have to prove the x equals 2 solution. This is not a light bulb question. Light bulb questions are long gone now. Okay, so what could I do? Now, I don't like exponents. I don't like my x values being up there in exponents. Makes me nervous. Don't like it. And looking ahead, just that b part, which is something you might want to get in the habit of doing for 8, 9, and 10. Often it's the same concept used for both parts of the question. This is especially true of 10, but we'll get to 10 eventually. But if you just a tiny little peek down in b, I can already see there's logarithms. So I suspect there'll probably be logarithms here. Okay, so should I apply logarithms right away? Should I manipulate this in some way and then apply some logarithms? So I might be tempted to split this into 2x squared and 5x squared and then group these together and get sort of two quadratics that might in some way have to be set equal to one another. Okay? And that's entirely a possibility. I don't think I'm going to do that because I think I'll have a couple more logarithms than I want sitting around. So let's ignore that for a moment. I'm not saying it's not doable. I'm just saying it's not something I want to deal with right now. What I think I'm going to do is I'm going to take log base 10 of both sides. Okay. Now, what logarithms do, in case you need just the tiniest little refresher, log base b of b to the, I don't know, a, is just a. Okay. Logarithms are a way for me to solve for x in the statement b to the x equals a, or something like that. Okay. And it's got a bunch of nice properties, and I do recommend you review them before you do the Euclid. Logarithms don't really pop up on Fermats or Hypatias anymore, but they are fair game on a Euclid, and you can usually spot a logarithm question on a Euclid. People like giving out logarithm questions because they scare people. They're a more recent concept, and we don't always have all the rules memorized. So I would say just about every year on a Euclid, you can either find a logarithm question or a question where they say, there is some function f of x that does this. That f of x won't necessarily be logarithms, but random functions that we don't have explicit formulas for also tend to scare people, I've found. Okay? And, if you find yourself having trouble with those questions, review logarithms. Get your hands on an introductory calculus textbook, go to the review section, and just go through every logarithm question you can. Go to all the Euclid questions, just seek out the logarithm questions or the there is a function f of x style questions. If you find yourself bad at something, embrace it and try and get better at it. Okay? So one of the nice things here is this log 10 and this 10 will cancel out, and I'll get x squared here. Now, logarithms of a product become a sum of logarithms. Okay, and now exponents can pop out of logarithms, so I can get x plus 2 times log 10 of 2. It's not the nicest thing in the world, but, that's okay. Log 10 of 5. And that's supposed to be equal to x squared. So now I'm going to get a quadratic. It's not going to be the nicest looking quadratic, but log base 10 of 5 and log base 10 of 2, these are just numbers. I can compute them on my calculator. I'll get decimal expansions out, but they are certainly numbers, and so this is just a quadratic. It's a scary looking quadratic to some people because it's got logarithms in it, but it's not that bad, I don't think. Minus log base 10 of 2 times x. I'm keeping these brackets here just to remind myself the x is on the outside. If you know what you're writing, go for it. It'll be a plus, because this plus and this minus turn into a plus when I bring it over to the other side. Log base 10, 5 of x. And then it'll be minus 2 log base 10 of 2. And minus 6 log base 10 of 5. And we can group things together. Plus log base 10 5 minus log base 10 of 2, all times x. There's nothing really to take out of here. I guess minus 2 log base 10 of 2 plus 3 log base 10 of 5. Now, remember what we said before, a log of a product can become a sum of logs. Well, I've got sums and differences of logs. I can recombine these, maybe make some nicer numbers. So 0, x squared, we had, it would be plus. We had log base 10 of 5 minus log base 10 of 2. So that can become log base 10 of 5 over 2. All times x. And then minus 2 times... Actually, you know what? I could have just simplified it. Well, we'll do it in 2 steps. That's fine. That's my mistake, not something you guys have to suffer through. So log base 10 of 2, and then it was plus 3 times log. So that'll be log base 10 of 2 times 5 to the 3, so that'll be 250. Okay. And then I can actually bring this 2 in here. So it can be minus, it'll become a square, because if I have k times log base a of b, that's the same as log base a of b to the k. So that'll be log base 10 of 62500. And now I don't need any more brackets. Alright, so we have a quadratic. Is it a particularly nice quadratic? But it's a quadratic nonetheless. Okay. So now, what can we do from here? Well, I would use the quadratic formula, plain and simple. So negative b plus or minus square root of b squared. Ooh, okay. I don't want to do logarithms squared. Is there... Whoops. And my pen has decided to act up, which it does from time to time. Keen observers will probably be able to point out all the times my pen has decided to just wig out. Okay, so maybe not the quadratic formula. Okay. So if I'm not going to use the quadratic formula, I'd like to be able to justify the x equals 2 a little bit better than just saying, well, I observed x equals 2. I mean, that does count as a solution, as a way to do it. I just don't think it's particularly elegant. So, is there something better we can do? I don't think the way I have it written now, x equals 2 pops out as a particularly obvious solution. And as a result, I don't like that. So here's the issue. I know x equals 2. If you've read their solutions, you probably know x equals 2. I don't read their solutions, but I observed it. But the question is, if I hadn't observed that, I'd be stuck right here, wouldn't I? And so if you're on a contest and you are not just, messing around and find, oh, x equals 2, how would, from this line, you proceed? Well, the quadratic formula, but as I said, that's going to lead to log base 10 of 5 over 2 being squared. I don't like squaring logarithms. That's the one thing I don't like doing. Add them, fine. Subtract them, fine. Multiply them, okay? And squaring, of course, is just multiplication. So, is there a good way to see that 2 works? And I don't think that there really is, and that's the problem. So, you can either say at this point, well, I know x equals 2 is an answer. I don't think that's very convincing. Or we could go back and say, well, is there something smoother I could have done? And so maybe the thing I originally dismissed of the writing this as 2x squared times 5x squared is the way to go. Okay, that's certainly possible. So I think that's what I'm going to do. I think I'm going to scrap all this work. I mean, it's fine work. I don't want to do a quadratic formula. I really don't. So, I wouldn't... First of all, I would not erase this yet. I would take a look at the, I'd look at the clock, or I'd ask how much time is left. Because, if there's not much time, don't go erasing a lot of good work just because you can't cap it off, just because you can't finish it off. Figure out, is there 10 minutes left? Can I work for 3 minutes and actually get a solution that sort of works on a scrap piece of paper? Then I'll erase it and transfer things over. Okay? But I've seen... people writing other contests or even writing tests as a proctor who, they don't heed the warning of 2 minutes left and they start erasing the big written questions. And I think, no, what are you doing? Yes, your answer wasn't going anywhere. Yes, a lot of what you had was wrong, but you could still get part marks and there's no way you're going to finish that 8-mark question in time. Okay? So, I wouldn't just erase this, but it's my video and I can go on as long as I want. So I will just erase this. And so instead, I'm going to start the other way, the way I said I wasn't particularly interested in doing. Still going to involve some logarithms, but okay, here we go. So, I'll bring the 2's over to the one side. So it's 2x plus 2 minus x squared. I'll bring 5's over to the other side, so this will be x squared plus x minus 6. And so here's what I don't like is this sort of situation, because again, if you're making assumptions about, well, it's got to be integers, you'll say, well, there's only way the only way you can have 2 to some integer equal to 5 to some integer is if they're both to the 0 and both of these are 1. And that's not going to go well for you. You'll get x equals 2, I believe. Yeah, 2 squared, but yeah, because 2 is the solution to both of those. But you'll be left a little stuck as to what's the second of our real solutions. So this is the sort of thing I was trying to avoid. What can we do? I suppose just do log base 2 of both sides. So that'll be negative x squared plus x plus 2 is equal to x squared plus x minus 6 times log base 2 of 5. Okay. But now at this stage, at least, I can say, aha, x equals 2 is a solution to both of these. I think that would be a bit more obvious. Okay, so this one over here is negative of x minus 2 x plus 1. Minus 1 squared, minus 1 and 2, yeah. And so this one over here is x minus 2 x plus 3 times log base 2, 5. Okay. But again, you're sort of plucking the x minus 2 out of thin air, and I'm not the biggest fan of that, but at least it's a bit more motivated here because they're very basic quadratics. And this is probably the way they want us to do it. So we'll bring everything over to one side. We'll get x minus 2, x plus 3, log base 2 of 5, plus x minus 2, x plus 1. Okay, so now I can take out the x minus 2 on both sides, and then we'll get x plus 3 log base 2 of 5 plus x plus 1. And so, we'll still get a quadratic, but I think it's a better quadratic because we've already got it one side factored, so we'll get another linear term, and that will all be fine. I just want to double check that I did copy this all correctly. Yep, okay, good. So, x minus 2, and then we'll get log base 2 of 5 times x. So it'll be plus 1. Plus 1 times x plus 1 plus 3 log base 2 of 5. Okay, and so x minus 2 here. So from this point we can say the roots are x equals 2 and x equals negative 1 plus 3 log base 2 of 5 divided by log base 2 of 5 plus 1. But I can simplify this because 1 is just log base 2 of 2. So I can say this last one here is negative 2 times 3, 2 times 5 to the 3, so that's 250. Over log base 2 of 2 times 5 is 10. And here's your very rare change of base formula. This becomes negative log base 10 of 250. And there we go. So these should be our answers. Now, log base 10 of 250, this is actually something I can grab my calculator for. So usually the log button, the one that actually says log, is just log base 10. So negative log of 250. So it's about negative 2.3979. But what I would do just to double check my arithmetic at the end is say, okay, let's save this value and let's see, does it actually work in the original question? Okay, does it work in the original expression? 2 to the x plus 2 and so on. So I'll write it down here so I don't have to keep re-entering it. I'm probably just going to cut it off here. Okay, so we need 2 to the power of negative 2.39794 plus 2. So that's about 0.75, they say. Times 5 to the power of 6 minus negative 2.39794. Okay. That's a really big number. That's 562,000 essentially. All right, so now if I log this number, I get 5.750, and if I square root that, I should get 2.39794. Okay, it all worked out. But I do that just to double check my arithmetic, especially if I'm someone who's nervous about logarithms, if those are the sorts of questions that really get me. Having my calculator handy and being able to say, okay, I got a solution that has a bunch of logs in it. Let's just grab the calculator, write down some decimals, and make sure this thing works out. Okay, if I'm really not confident in my ability to simplify logarithms. Okay, and I would suggest you simplify them. I would not leave it like this. I'd leave it like this. So you might have a little summation of, therefore, x equals 2 or negative log 10 to 50. I suppose you could also write you could write log 10 of 1 over 250 if you're that sort of a person. But I think negative log 10 to 250 looks a little better. Okay. So that was just A part. We've still got B part left to go. And we do have our 2 real solutions there, by the way. Don't need to justify the 2 real solutions because they told us about them. All right, B part. Determine all real solutions to the system of equations of more logarithms. Okay, yep, already noticed that. And prove that there are no more solutions. So this might be a little harder. We'll probably get, 2 or 3 solutions. I wouldn't expect a whole ton of solutions. I wouldn't expect a family of solutions, just from experience. But we'd have to prove that there, once we get our 3 solutions, we'd have to prove there aren't more than those 3, or however many solutions there are. I would expect at least 1 solution. Possibly it's one that we can find just by, randomly guessing or something like that. But what have we got? We've got x plus log 10x equals y minus 1. Y plus log 10 y minus 1 equals z minus 1. Z plus log 10 z minus 2 equals x plus 2. Okay, interesting. So some things I'm observing. There's no z's in this equation, there's no x's in this equation, and there's no y's in this equation. It's a bunch of x's equals some y. A bunch of y's equals some z. A bunch of z's equals some x. So it's sort of cyclic in a way. It's not entirely symmetric. If it were x plus log x equals y plus log y equals z, that would be nice and symmetric. And so, if you get one solution, there's probably 6 more or something, or 5 more lurking around. But we don't have that. So I make that observation, and I'm going to start copying this down into my notebook. Now, something to note, especially because we've got a system of equations here, I would strongly suspect that we don't have to use... Is it z minus 1? I think it was z minus 1. I would strongly suspect that we don't actually have to use the fact that it's base 10 here. I think that I definitely don't think we should be raising any of these things to the power 10. I might be wrong, but I think we're just going to be exploiting properties of the logarithm. I think is it x? X plus 2. I got most of it right. Okay. So, well, just off the top of my head, if we're exploiting properties of logarithms, a common thing to do when you're using systems of equations is to add up everything. And when we add logarithms, we get to multiply their insides. So this is actually x times y minus 1 times z minus 2. And the nice thing over here is the plus 2 and the minus 1s will cancel, and we get x plus y plus z. So that cancels out with that. And so we get log base 10 of x, y minus 1, z minus 2 is 0. And that tells me that, well, there's only one number that gives me a log base 10 of that number being equal to 0, and that's 1. So that's pretty nifty. All 3 of these numbers multiplied together are 1. Now, this isn't our original y and z. Okay, we've got y minus 1 and z minus 2. And we're not really going to be able to get away from that. You're always going to have a y minus 1 and a z minus 2. And the reason being, this log here really sort of traps these numbers. There aren't really properties of logs where I can do something with, log of a plus b, and I can add something or I can multiply something, and suddenly I can get rid of the b. Okay, there's nothing I can do to this that is reasonable to get rid of a plus b. So this minus 1 and this minus 2 are sort of here to stay. Okay, the way I always think about it is they're sort of trapped behind the log 10. They've been stuffed in log 10 prison or put in the log 10 box. And it takes a lot to unpack that box and get at the y minus 1 to change it to a y. See, that first equation there, x plus log 10x, is very nice looking. Okay, but we don't have y plus log 10y. We've got y plus log 10 y minus 1. And so if I wanted to just get rid of that minus 1, just talk about y, that's going to be pretty hard. Same with the z minus 2. But it's almost easier to get a minus 1 with the y here. And so that might not be a bad thing to poke around with. I'm going to drop the 10 just as I write. No, I'll keep it in. But it's okay to drop the 10. There's only ever going to be log base 10 in this question. And it's actually common practice to not write the 10, especially if you're an engineer. So this is y minus 1. And we've got y here. I'm going to subtract 1 from both sides. So we've got z minus 1. I'll do it in light blue. A minus 1 here and a minus 1 here. So now it's the same thing and then log of that thing. And we had z plus log base 10 of z minus 2 is x plus 2. And so to make it match with this inside thing, because I can't really change that, but I can change this. I will subtract 2 from both sides. So this gives me a new set of equations. And, oh, that actually looks really nice. Because we get z minus 2, and then we have z minus 2 down here. So I think what will probably end up happening is we're not going to solve for x, y, and z. We're going to solve for x, y minus 1, and z minus 2. And then from there get x, y, and z. Because now these are looking really nice. I'm debating whether or not to introduce a... I think introducing a new variable is called for. So I might say something like, let u be x, I guess, v be y minus 1. I could just let x be itself, but I like that the numbers are increasing, or the letters are increasing. Okay, so we make this statement very clear. Then we get, and it's always a good idea if you can to number your equations. So we get, it's not x anymore, it's u plus log base 10 of u is v. V plus log base 10 of v is w. And w plus log base 10 of w. Now I'm regretting the w because the pen does not like the little dip I make for the w. Is going to be u. And so this is nice and symmetric. And so if I were able to show that, u could be 1 and v could be 5 and w could be, I don't know, -2 or something. Doesn't really matter what they are. Oh, no, I guess it can't be -2. Let's just call it 1/2 then. But just to use sort of numbers that are vaguely associated with with 10. If this were a solution, then it would turn out that this is also a solution. And so there's a great deal of symmetry here. And that's pretty nice. Okay. Because there's no way to tell, oh, u must be the smallest number, because it's not. Okay, there's a great deal of symmetry here, and that's nice and exploitable. This is a desirable thing to be looking at here. Now, I can make the same observation that I have already made, which is u plus v plus... If we just add up both sides, we can still observe log 10 of u, v, and w is 0, so u times v times w is 1. Okay. So, is there... So I'm trying to think where I might be able to go with this, because the problem is I've got 3 variables. So I suppose what I could do is I could maybe say, well, let u be fixed, and then v is going to be u times r, and then w is u over r. So, actually that's not a bad idea. So let r, the ratio, be such that v is u times r. Actually, you know what? I'll make v the middle one. So u is v divided by r. V is obviously v. And w is v times r. Oh no, they're not in geometric sequence. No, silly me. Okay, that didn't work. And that would work if v were 1. Can v be 1? If v is 1, then we'd have 1, and then log of 1 is 0, so we'd have w is 1, w would have to be 1, u would have to be 1. So if they're all 1, that works. Okay, so that's a solution. Not a very inspired one, but there might be more that we would have to figure out. I guess all we can say here is w is 1 over uv. Now, can I plug that in somewhere? and make things a bit more interesting. Well, okay, before I get to that, I am going to write down that I do have the one solution. Observe that u equals v equals w equals 1 is a solution. Our quest is to find the others, if indeed there are others. And that of course, is the challenge. Well, let's try w equals 1 over uv. It might be due to the highly symmetric nature of this that there just isn't one, but so we'll plug that into 3 and 2. So, we get the new 2, which is v plus log 10v is 1 over uv. And we get the new 3, which I'll call 3 prime, is 1 over uv plus log 10 of 1 over uv is u. Now this 1 over I can switch. So I can say this is 1 over uv minus log 10 of uv equals u. And so maybe I have to multiply these expressions. I'm not entirely sure what I want to do. Multiply both equations by uv. I don't see that going anywhere either. So this has, we'll put a little pin in this. We'll come back to it, but it seems like it's going to get out of hand to multiply both of these equations by uv on both sides. Because I'll get a uv squared up here, but I'll get a u squared v down here, and that's not really going to match up in a particularly helpful way. Although, hang on. So we'll change this guy to, he's still a u. So I can rearrange this and say 1 over uv is u plus log base 10 of uv. I'm going to call this equation 4. And now, by combining these two, we get v plus log base 10 of v is u plus log base 10 of uv. But this is a product. So now I can cancel them out, and fantastic, it's the first equation again. Darn it. You can find this happens a lot, especially when you have a nice list of symmetric equations, that you start trying to do something, and you do 10 lines, and you think it's brilliant, it's starting to come together, and then, it's just one of the other expressions, and that seems to be what we've got here. I really thought that was going to go somewhere. It didn't. Okay. So what can we do? Well, let's get a fresh sheet of paper. I'm starting to think that maybe 111 is the only solution. Now, I haven't been tinkering with questions super long, but I find for the questions where it's find the solutions and show there aren't many more, that usually you can find all the solutions that there are relatively quickly. Now, I observed the 111, and nothing else is really springing to mind. So maybe there aren't other solutions. And this is not an unreasonable thought to have, even if we don't have a lot of contest practice and think, well, no, these answers should be pretty apparent. Sometimes you're just not seeing the right thing. I might just not be seeing the right thing, and this video will go on for another hour. I hope not. The only ones I like going on forever are the Euclid 10s and the Canadian Senior B3s. Those can go on for 4 or 5 hours it doesn't really matter. But if I started now trying to prove that 111 was the only solution, maybe maybe somewhere in there I'll reach a point where it can be either this or this, and maybe that will yield another path to another set of solutions. But right now I'm not seeing any other solutions, so perhaps we try. Okay, so is 111. Keep in mind, if 111 is the only solution, I still haven't written out my solutions for x, y, and z. Okay, this is x, y minus 1, and z minus 2, so I guess it would be 1, 2, 3. So we ask ourselves, is this the only solution? Well, suppose not. So by symmetry, let's say u is not equal to 0. Now, my equations here all have logs in them. So to apply log, we know that u, v, and w are all greater than 0. Okay, you can't plug in a negative number or even 0 into a logarithm. You can get those numbers out of a logarithm, sure, but you can't plug those numbers into a logarithm. So u isn't, I don't know why I didn't say u isn't 0. I was probably thinking ahead already. U isn't 1. Well, let's just assume that. Then at least one of v or w also isn't 1, because you can't have a product of 2 1s and a not 1 and still be 1. Now, how will this impact things? And I want to be sort of thinking about log properties. If u isn't 1, u's got to be greater than 0. What if so u is either greater than 1 or u is between 0 and 1. Okay? And if it's between 0 and 1, then log base 10 of u is negative. So then u plus log base 10 of u equals v implies that u is greater than v. Because all these equations can be, yeah. I think there's a better way to say this. So I got these equations here. So rewriting, I'll call it u 1 prime, 2 prime, and 3 prime, because the other ones didn't really work out, so I wouldn't be writing those down. But u minus v is log 10u. V minus w is log 10v. And w minus u is log 10w. And so I think what we're going to show is that if u is less than 1, then v is less than u, and therefore also less than 1, and so w will be less than 1. Yeah, I think this will work out. And probably something something similar would have to happen for... Okay. So if I'm even so here we're in the writing up stage. I'm trying to be as elegant and as simple as possible. So I'm not going to say by symmetry. Okay, so I know that each of these numbers is greater than 0. Okay. Okay, so if u, v, and w are not 1, 1, 1, then at least one of the values is greater than 1, and one of the values, and at least one of the values is less than 1. Okay? If you wanted to, you could prove this, if p is greater than 1, q is greater than 1, and r is greater than 1, then pq is greater than 1, and pqr is greater than 1. So how could their product be equal to 1? That's the idea. So it's not so much of a stretch to say, well, one of these values has to be greater than 1, another one has to be less than 1. You could have two values be less than 1, but you can't have all three be less than 1, because you can't have a product of numbers less than 1 being actually equal to 1, as long as they're positive. Yeah, you could have two negative 1s and an actual 1. So let's say is between 0 and 1. So at least one value is bigger than 1, at least one has to be between 0 and 1. Because all these values are positive. Okay. So let's be, really, really mathematical sounding and say, without loss of generality, which basically means we're going to make this choice, but it doesn't matter because it's just a name. Without loss of generality, suppose u is the one that is between is at least one of the ones that's between 0 and 1. Then log base 10 of u is less than 0. So by 1 prime, u minus v is less than 0. And so u is less than v. Did I do something? No, it's v minus u. V minus u. V minus u is less than 0. I had a bit of a panic there. So v minus u is less than 0. And so v is less than 1. But that tells me 0 is less than v is less than u is less than 1. So log base 10 of v is less than 0. By 2 prime, then w minus v is less than 0. So w is less than v. But then all of them are less than 1, which is a contradiction. You can't have a product of things that are all less than 1 and positive be equal to 1. So just remember u, v, w equals 1. u, v, and w all have to be positive. So this is an impossibility. Right, there we go. And I got these wrong. I copied these wrong. It's v minus u. The u comes over to this side. W minus v. U minus w. So there we go. We could even, I suppose, with 3' go a step further and show that u then had to be less than w. And then, so how could u be less than w, less than v, less than w, less than u? Then u would be less than u, and that's also impossible. But I'm happy with this one right here. So, to conclude, this is the only possibility. Now remember, x is u, y minus 1 is v. So y is v plus 1. And z minus 2 is what we call w. So z is w plus 2. So x, y, z is 1, 2, 3 is the only solution. And there we go. We did a little proof by contradiction to show 1, 1, 1 is the only option for UVW. All right, not bad. And that finishes up question number 9. Up next will be the one we already have arrowed, question number 10. And, well, we'll dive into that later, but it looks like a lot of fun with triangles. I will see you guys for that in the next video.